Welcome to STEM Career, make everything science, technology, engineering, mathematics easy to comprehend, assimilate, fun, and entertaining. Now, let's do circle theorem. And these are things that have been worked out so that when you come across anything with this theorem, you can easily bring out your answer without doing any stressful work. Just by observation, you can bring out your answers. Now, we talk mainly about angles to start with, and then we talk about some length and measurements. We know that in circle, the distance from the center to the circumference is always equal. And the first theorem I would like to talk about is about the relationship between the angle at the center and the angle at the circumference. The angle at the center, this is the center O, and this is the circumference C. So, it is observed that the angle here will be twice the angle at this place. Please take note of one thing. The two legs originate from the same chord, from the same segment. Let me put it that way. From the same chord or from the same segment. That is this place and this place, to the center and to the circumference. So let me call this place A, B. So the first one to be dealt with is that the angle subtended at the center of a circle is twice the angle subtended at the circumference. Now, let's deal with it like this. Let's call this place F. And we know that in a circle, the distance here, R, is equal to the distance here, R, and is equal to the distance here, R. Now, since we have cut this into two, let's give this angle here, alpha. Let's give this place beta. And you can see that it is isosceles triangles. In this place and this place are equal. It means that these two base angles will be equal. So this place will be alpha. This place and this place will be equal. This place will be beta. You can see. So let's prove. Let me quickly put that into writing. Angle OCA is equal to alpha. Therefore, angle OAC is also equal to alpha. Isosceles triangle. Same way, angle OCB is equal to beta. Therefore, angle OBC is also equal to beta. Same condition, isosceles triangle. That's for you. No stress. And we also know in a triangle, the angle, exterior angle, will be sum of the opposite angles. You remember, when you have a triangle like this angle here will be equal to this one plus this one. Because everything is 180. So this one is plus this one is 180. This one plus this one is 180. So this one will be equal to this one plus this one. Simple. That's just the logic. Therefore, this place here now, we can say this place is equal to 2 alpha. And this place is 2 beta. You can see now. Therefore, angle FOA is equal to angle OCA plus angle OAC, which is equal to 2 alpha. In the same way, we can also say angle FOB is equal to angle OCB plus angle OBC, which is equal to 2 beta. So you can see, with this, therefore, angle AOB is equal to angle FOA plus angle FOB, which is equal to 2 alpha plus 2 beta, which is equal to 2 into alpha plus beta. Therefore, angle AOB is equal to 2 into angle ACB. So that is proved already. So anytime you look at any question that comes like this, when they are asking you a question on angles in the circle, the first thing you should go and check the relationship. If you have a center, is there any angle at the circumference? Quickly check. That is the first thing I always look for. Now let's look into the next one. So what I'm trying to say is this: if you have a question like this, first of all, look, have they given you angle at the center or at the circumference? Quickly go straight to the center. If you are given angle at the center, quickly go to the circumference and then half it. Or if it is at the circumference, you go to the center, double it. Then you start looking for other things to solve your problem. So with the first theorem you have checked now, you can also confidently say that angle in a semicircle is 90 degrees or right angle. What do we mean? This is what we mean. That if we have it like this, or we cut it like this, you know, half of it will be semicircle. We are saying that this angle here is 90 degrees. That's what we are saying. So from the first theorem that we have proved, we can confidently say that the angle at the circumference here is 90 degrees. Because this one is 180 degrees. So we can now say, let's say this is A, C, B, O. So A, O, B angle is equal to 2 times A, C. And this is angle in a straight line. AOB is equal to 180. This angle in a straight line. So from this, you can just conclude that 180 is equal to 2 times angle AC. So ACB is equal to 180 over 2, which is 90 degrees. So you can see everything will be coming out from the other theorem. Now let us look at another theorem. This says that angles in the same segment are equal. Angles in the same segment are equal. What does this mean? Look at this chord. It might be drawn, it might not be drawn. You know, we talked about segment the other time. Now let us now generate lines from the segments to the circumference. Let's make this A, B. Let's make this one C. Let's do this again. A, B, C. Let's call this one D. You understand? Now let me now remove this. You might put it, it might be there, it might not be there. But let us assume you are not given. Because the two of them start from the same line points, it means that they are in the same segment. That is, the same line that cuts the circle. They are generated from the same lines. So you can see it was there. I deliberately removed it just for you to know how to visualize it in case you come across it in the examination. Now, but we have already learned something, that when we have this angle here, let's call this one 2 theta. Automatically, if you generate lines from here to here, lines from here to here, even from here to another place, let's call this one G. Please, this one is G. Let's call this one E. Are you getting it? So let's call this one alpha, beta, theta. From our knowledge, we know that. Oh, sorry. We know that. Let's call this one gamma. Let's call this one gamma. From our knowledge, that angle at the center is equal to 2 times angle at the circumference. You can see. It means that gamma, sorry, this place will be O. A, O, B, gamma is equal to 2 angle A, C, B, which is equal to 2 times angle A, D, B, which is equal to 2 times angle A, E, B. Do you understand? So it means that gamma is equal to 2 alpha is equal to 2 beta is equal to 2 theta. Therefore, alpha is equal to beta is equal to theta. So once it is in this circle and it is generated from the same points around the circle, all the angles will be equal. This is peculiar to circle. This is part of the way you can use to define a circle. Apart from radius, that it always has the same equal distance from the radius. You can also use this to define a locus, that is motion along the surface. That is, from 2 points, the angles will always be equal. Aha! I just think I should not rush out of this theorem. That this angle at the center is equal to angle twice the angle at the circumference. It will not always be to the top. It might even come below the diameter, like this. You know, it can go like this. It can come like this. It can even go like this. So let us start from the one that comes below the radius. Let's talk about the one that comes below the radius. What the theory is saying is that this angle here, that is this, will be twice this one. That is what it is saying. Now let's quickly look at it. Let's place this A, B, O, and B. And since we have it like this place is R, this place is R. You can see. And this place is also R. Let me make it capital. Let this place be alpha. This place will be alpha. You see? This place is alpha, this place is alpha. So invariably, this place will be beta. And this place here will be beta. But this is the angle we are talking about. Beta minus alpha. That this angle here will be equal to. Let's see what it will be. Now, since this place is alpha and alpha, let me write it down. Angle OAD is equal to angle ODA. OAD, sorry. OAD is equal to angle ODA is equal to alpha. In the same way, angle OBD, sorry, is equal to angle OBB. Same condition. Isosceles triangle. Now we have known that from triangle, angle B, let me make this is BOF is equal to 2 beta. Exterior angle of triangle. The same thing here. Angle BAOF, this place, is equal to this one plus this one, 2 alpha. Exterior angle of triangle. Now, this angle here, angle AOB, that's the one we are looking for. So angle AOB will be equal to angle BOF, angle BOF minus angle AOF, angle BOF minus angle AOF. Please look at it. BOF minus this one. This is the angle I am talking about here now, which is equal to, and you know, we have gotten this one here. AOF is this. So 2 beta minus 2 alpha. And you remember, I told you that the angle at the circumference we are talking about is angle ADB. So which is equal to 2 times angle ADB. You can see. So under all circumstances, angle at the circumference is twice the angle at the center is twice the angle at the circumference, in as much they are in the same segment. I will give you another type of circle that you might come across. Now look at this one now. What I want to show you is this. What I want to show you is this. If you are talking about half of the angle at the circumference, it will be the one opposite the angle at the circumference. So that, like this one here, is never equal to this. It will be here. that will be equal to this. So you understand? It will be this one beneath that will be equal to twice the angle at the circumference. I want you to take note of that so that you don't make that mistake. Anytime you are doing this work, look at this one here. The one that will be down here will be the double of it. For this one now, so this place will be equal to 2 alpha. Take note of this. We approve this one. Now let's look at this one now. Let's look at this. We have this one here. Now let's cut it. This place is R, this place is R. This place also will be R, as we have said before. And let's cut this one down like this. Let's make it F. Here, if this place is alpha, this place will be alpha, just like in the first one we did. This place will be beta, this place will be beta 2. And if you look at it, FOR here, FOB, this place will be equal to 2 beta. This place 2 will be equal to 2 alpha. And the angle here, ADB, is equal to alpha plus beta. And angle AOB, from the proving, is equal to 2 alpha plus 2 beta, which is 2 into alpha plus beta. Therefore, angle AOB is equal to 2 times angle ADB. So, from the figure, you can easily decipher it. And if you want me to write it out, I can easily do that. But from the ones you have written out, I don't think that's necessary again. Oh. Now let's talk about cyclic quadrilateral. The next theorem is saying that the opposite angles of a cyclic quadrilateral are supplementary, that is, they add up to 180. You will see what happens. Cyclic quadrilaterals are quadrilaterals whose vertices are all on the circumference of a circle. Now look at it. If you have 1, 2, 3. This is a cyclic quadrilateral. Any quadrilateral that can fit inside a circle and all its vertices will be on the circumference are described as cyclic quadrilateral. You have so many. Now, look at this. Let's label A, B, C, D. We know that the angle here, the total angle here is 360. Now, let's call this place alpha. Let's call this place beta. We can say that this place is 2 beta. And this place is 2 alpha. You can see. And you know that 2 beta plus 2 alpha will be equal to 180 degrees. From the previous theorem, you know, angle at the center is double the angle at the circumference. So this one is equal to double of this, this one is double of this. So 2 beta plus 2 alpha is equal to 180 and 360 degrees. So 2 beta plus 2 alpha is equal to 360 degrees. Therefore, beta plus alpha is equal to 360 over 2, is equal to 180 degrees. Therefore, opposite angles of a cyclic quadrilateral adds up to 180 degrees or are supplementary. So in the same way, this angle here and this one will be equal to 180 degrees. Now, let's look at another aspect. Since this place and this place are equal to 180 degrees, this place here, if you extend this place, the exterior angle here will be equal to 180 minus beta. Do you understand? And that will be equal to alpha. So exterior angle, therefore, exterior angle is equal to opposite angle of a cyclic quadrilateral. So you can see it's formed.